Okay, bonding, specifically ionic bonding. To recap a previous video, ionic bonding occurs between a metal or a metallic species and a non-metal or a non-metallic species. Metal, non-metal. Why is this? As you probably already know, the underlying reason that a metal is that it has a tendency to lose electrons. So metals are going to lose electrons. This is because in general they have a less than half filled outer shell and it is energetically favourable for them to do so. Whereas a non-metal, well, they're the opposite though, so they have a tendency to gain electrons or electrons. Why? Well, in general they have a greater than half filled outer shell and it is energetically favourable for them to do so. So the process of ionic bonding is actually very simple. Electron or electrons are transferred from the metal, and we'll draw diagrams of this in a moment so you can see this, to the non-metal, forming oppositely charged ions. And those oppositely charged ions attract each other, and that attraction is the ionic bond. So if we look at the next bit, the definition, you'll see that I've already written in the electrostatic force of attraction between. That is because all the types of bonding you're going to look at, the definition starts with the electrostatic force of attraction between, because a bond is an electrostatic force of attraction. What differentiates between the different types of bonding is what that force is acting between. So let's just go back. We have a metal and a non-metal. The metal is going to lose electrons. The non-metal is going to gain electron or electrons. So the metal transfers electron or electrons to the non-metal. So the metal becomes a positive ion called a cation because it has lost negative electrons. The non-metal becomes a negative ion called an anion because it has gained electrons. So we have oppositely charged ions. So therefore, the electrostatic force of attraction between oppositely charged ions. And I've explained how those are formed, but we'll see in a sec below. Let's just get straight on with that, shall we? Let's have a look. I've got two examples here, lithium oxide and magnesium oxide. First thing I need to do before I get to drawing diagrams and showing you what's going on is I need the formulae of these compounds. I need these formulae because I need to know how many of each type of species are involved. This is ionic bonding, so I'm going to use the crossover rule. If you're not familiar with that, go back, look at the previous videos. So, lithium oxide, Li, it's the symbol for lithium, and it is in group 1, so it's going to be a +1 ion. Oxygen, just O, just the symbol, and it is in group 6, so it is going to be a -2. Draw my line underneath, take down the size of the charges, cross them over, 2 and 1. Lithium oxide is going to be Li, how many Li's? 2. O, how many O's? Just the 1, so I don't draw it in. Always, always worth drawing out your crossover rules in full and properly. I always see people taking shortcuts. Do it properly, it will pay off in the long run. So, lithium, electronic configuration, 2, 1. Oxygen, electronic configuration, 2, 6. Now, I'm going to draw those out for you. So you can see I've drawn out lithium and oxygen. Now, let's just check that we're happy with that. Lithium 2, 1. 1, 2, that's the 2. 1, 2, 1. Oxygen, 1, 2, that's the 2. 1, 2, 3, 4, 5, 6. So, jobs are good and so far by the looks of things. However, let's just look back at the formula. It is Li2O. Li2O, which means that for this to work, I need 2 lithiums for every oxygen, which I will now draw in for you. Why is it important to have 2 lithiums? Well, we're looking at transferring the electrons. The metals, i.e. the lithiums, are looking to lose electrons because it's energetically favourable for them to do so, and the oxygen is looking to gain electrons because, again, it is energetically favourable for it to do so. In doing so, they will end up with complete outer shells. So let's look at this transfer. Lithium has an outer shell electron, 1 outer shell electron. That is going to be transferred into this gap on the oxygen. It hasn't gone there yet, but it will go there. If we add that electron in on the oxygen, that means the oxygen will have 7 outer shell electrons, still not complete. So we're going to take the electron from the second lithium. Let's transfer, it's complete transfer, this electron into that gap there. This will give us our ions, our positive lithium cations and our negative oxygen anion, and I'll draw them for you. Okay, so I've drawn the ions in, but they're not finished by any means. I've got a few more things to do, but I thought I'd talk it over with you. So the lithiums, they've transferred their outer shell electrons. Let's just check, where did that outer shell electron go from the left-hand lithium? It went in here. So I draw it in as a cross. It is still a cross because it came from the lithium. That way I can keep track of where the electrons have come from. Equally on the other side, so follow the other green arrow, I have another cross here. These things, however, are ions, so they have charges. Lithium has lost 1 electron, and we can see up here that the lithium ion has a charge of +1, so I need to show that, so I draw a square bracket all the way around and draw a +1 up in the top right where charges go. Let's do the same for the other lithium. +1 up there. And the oxide is -2, so let's draw square brackets and -2. What else can be said about this? Well, if you are asked to just draw the ions, you may draw them like this, as I have shown. You may draw them leaving out one of the lithium ions and drawing a big 2 in front of the other one. You may be asked to just show the outer shell electrons. If you're just asked to show the outer shell electrons, then you will be seeing something like this. No difference for the lithium, but the oxide ion will look slightly different because, of course, it has more than 1 shell. So if we're just drawing the outer shell for the oxide ion, we're just going to be drawing the outer shell, which is going to look like that. Let me get the blue pen. And we're going to have these 6 electrons, which the oxygen brought along on its own anyway, and the 2 electrons transferred from the 2 different lithiums. And we would have a -2 charge. So if we're showing outer shells only, the oxide ion will look like this. If we're showing all the shells, the oxide ion will look like this. And the only way you know that is reading the question very carefully. Now, I'm going to do an example for the magnesium, and I'm going to do a similar set of diagrams, which I'll just draw fully in, and then I'll do a little bit of a talk over as to how you would describe both of these in words. Okay, so magnesium oxide, MgO, drawn below, magnesium 282, oxygen, as before, 26. So let's see the transfer of the electrons. Remember, the metal loses electrons because it's energetically favourable to do so. The non-metal gains them. This leaves us with the oppositely charged ions, which attract each other. So we have to transfer those electrons. Transfer from the magnesium, 1 electron is going to go across. That's 1 electron being transferred. And a second electron is going to go across. A second electron is being transferred. We have to show, if we're drawing these sorts of diagrams, the electrons being transferred individually, so an arrow for each electron. Okay, I'm going to draw the products out for you now. So they've popped up for you. Things to note. Things to note on this, well, the magnesium, I only needed one of it because the formula was MgO. The oxide, I only needed one of it because the formula was MgO. The charges, why is the magnesium +2? Well, if you look above, the magnesium has transferred 2 electrons. Lose 2 electrons, become +2. The oxide is -2. Why? Gain 2 electrons, become -2. As you can see here, I have left in the inner shells. If you were asked to show the ions with just the outer shells as before, you would leave out anything other than the shells round the outside. Now, you may sometimes be asked to describe this process in words. So, let's have a look and see what happens. The magnesium has fully transferred 2 electrons to the oxygen, leaving 1 Mg2+ ion and 1 O2- ion. I'll write that down for you in a sec, but let's just see what I've talked about. I've said how many electrons are being transferred, and I've talked about the direction of the transfer. 2 electrons from the magnesium, so that's the number of electrons, going to the oxygen. Direction of transfer. And then I've told you what I've got. An Mg2+ and an O2-. Let me write that in. So I've written that in for you. Now let's have a look at the key marking points. We said we needed to know how many electrons were being transferred. 2 electrons. Okay, we said we needed to know the direction of travel. Those are the green arrows. To an oxygen. And then we needed to know what we formed. We formed 1 Mg2+ ion and 1 O2- ion. Much easier here to write these as Mg2+ and O2- rather than trying to write magnesium ion and oxide ion, because the examiner will be looking for the charges as well. I'm going to talk you quickly through the same deal with the lithium oxide one on the left, but I'm not going to write it in because it might be a good idea for you to write it down for yourself. So let's just have a look. This time we have 2 lithium atoms, each of which transfers 1 electron. And here you can put in brackets, i.e. 2 electrons in total if you wish. 2 lithium atoms, each transferring 1 electron to 1 oxygen atom, leaving 2 Li+1 ions and 1 O2- ion, which is just describing what you see in the diagram and covers the marking points of how many electrons, direction of travel, and what you end up with. So, ionic bonding. Quick recap. Ionic bonding occurs between a metal and a non-metal. Why? Metals have the tendency to lose electrons, non-metals have the tendency to gain, which is a very nice situation because the metal can transfer the electron or electrons to the non-metal. We need to get the ratios right so that everything ends up with the full outer shells. We work out how many ions we have by doing the crossover rule and looking at the formulae. And those oppositely charged ions that we end up with after the electron transfer, they attract each other because they are oppositely charged. Opposites attract. And therefore the definition of the ionic bond is the electrostatic force of attraction acting between oppositely charged ions. Go away, make your own notes, practice this, do other examples, and get your head round ionic bonding.